Okay, so once more, good morning. As I mentioned today, we will continue with discrete time unit impulse and unit step sequences. First, discrete time unit impulse signal is simple. It's very easy as written here. So it is 1 when n equals to 0, and it is 0 otherwise. So how can we plot the signal? If you want to plot this, it is simply, if this is n, impulse of n is simply 1 at n equals 0. So this is how impulse of n is shown. What about discrete time unit step signal? Well, it is again simple. If n is larger than or equal to 0, it is 1. Otherwise, it is 0. So let's plot it. 0, 1, 2, 3, 4. So it is always 1 for n larger than or equal to 0. So these are all 1. And it goes on like this. So these 3 dots represent that it goes on like this till infinity. So these are very easy and very basic signals. They are quite important for us. We will see them especially when we study those convolutional operations. Well, how they are related? Well, I can write impulse of n in terms of un. It is simply un minus un minus 1. Well, how can you see this? Actually, let's plot un. 0, 1, 2, 3. So this is my un. What is un minus 1? Remember? What is un minus 1? It is shifted to the left, to the right, sorry, by 1 unit, right? So this is 1, this is 2. These are all 1, by the way. 3. It goes on like this. If I subtract the lower one from the upper one, what do I have? Those cancel, right? So I simply have this impulse of n. Okay, so this is quite simple. What about un? Un is simply impulse of n. If you check this un, what can you say? This is nothing but impulse of n, right? What about this one? The second one is impulse of n minus 1. So it is impulse of n shifted 1 unit to the right. So u of n is simply impulse of n plus impulse of n minus 1 plus impulse of n minus 2 plus, it goes on like this till infinity. So it is simply equal to summation m from 0 to infinity impulse of n minus m. So this is how can I write simply un in terms of impulse of n. So what about the next relationship? So if I sum impulse of k from k equals k1 to k2, what is it? So I have impulse of k, and I simply sum it from k1 to k2, and this is simply u of n minus k1 minus u of n minus k2 minus 1. So I simply sum those, let's say, impulses in a predefined interval. So that's it. What about the next one? X of n is equal to impulse x of n times impulse of n minus n0. So let's write here. Assume that I have such a general x of n. So let's say this is my x of n, and this is simply 0. So I will multiply this by impulse of n minus n0. What is impulse of n minus n0? It is impulse located at n0, right? So this is impulse of n minus n0. It is the simple impulse of n shifted by n0 units. Okay? So it is either to the right or to the left. So if I multiply those two, what do I have? if I multiply those two, I will have here impulse of n minus n0 scaled by x of n0, right? So the result is simply x of n0 times impulse of n minus n0. So that's it. I will scale this impulse of n minus n0 by x of n0 here. So what about the next one? Summation k1 from k1 to k2 x of k times impulse of k minus n0. So what is, by the way, what is this impulse of k minus n0? So it is simply equal to 1. So this impulse of k minus n0. So impulse, if inside the parenthesis is 0, impulse has value 1. So just like here. If n is 0, impulse of is 1. If this equation here, k minus n0, this relation is 0, then it means that k minus n0 is equal to 0, then k equals n0. So if k equals n0, then this relationship is equal to 1. So this term here must be equal to 0 for this relation impulse of k minus n0 to be 1. So what does it tell you? So if k equals n0, this is simply 1. So I multiply them and sum. Since there's a summation, the result will be just a number, not a graph, just like here. So here you see the result was a graph. So it was simply a signal impulse of n minus n0 times x of n0. But since now there's a summation, I will multiply them and sum. So let's draw it here. Let's say here this is with respect to k, and I have those xk values. So let's say this is from k1 to k2, and now I have this. So this is x of k, and this is impulse of k minus n0. So what is it? It is simply at n0, right? So if you multiply those two, the result is non-zero if this n0 is in the interval k1 to k2, right? So if n0 is outside this interval, when I multiply those two signals, the result is simply 0. So this is equal to simply, so when I multiply them, this is 1, impulse of impulse of k minus n0 is 1 at k equals n0. So when I multiply those two, let's say that this is n0 and this is x of n0. If I multiply those two, the result is just like here, just like the upper one, right? It is x of n0 times impulse of k minus n0. So I multiply them and sum. So this is multiplied with 0, this is multiplied with 0. So all of the other terms are multiplied with 0, but I only have this term in the middle, right? So x of n0 times impulse of k minus n0 and sum is simply x of n0 if I have k1 smaller than equal to n0 smaller than equal to k2, and it is 0 otherwise. Okay, so that's very easy. Now I have another relation here. Those two are your exercise actually. Please try them at home. And if you do not get the results, please get in touch next week. But these are your homeworks. Well, the discrete case, unit impulse and unit step sequences are quite easy because they can be visualized by just as sequences. But in a continuous case, now we should make some tricks in order to define those unit impulse and unit step signals. By the way, I hope you can hear me. Please write to the chat if you cannot hear me. In order to understand those continuous time unit step and impulse signals, well, we will first start with some definitions. First, I will define impulse delta of t. So this is how I can define impulse delta of t, and this is simply my u delta of t. So before defining continuous time unit impulse and unit step signals, I will first define two auxiliary, let's say, signals. First one is impulse delta of t. It is 1 over delta for the interval 0 to delta, and the next one, u delta of t, is increasing from 0 up to 1, and it is equal to 1 at t equals delta. So these are my first very basic signals. Then, of course, this is the relationship between those two. Impulse delta of t is equal to du delta of t by dt. So if you take the derivative of u delta, then it is simply equal to impulse delta of t. So these are, by considering these, I will define continuous time ut and delta t. Well, first check that. So this is the important relationship between those two. But another thing that I consider is this. This impulse delta of t has unit area. So if I integrate from minus infinity to plus infinity, this impulse t dt, this is simply equal to 1. So the area here, the shaded area, is equal to 1. So as I change delta, as I increase or decrease delta, regardless of delta, this area is always 1. So we will use this actually. So as delta goes to 0, so what happens? So let's once more plot this 1 over delta impulse delta of t. If I increase delta, what's happening? Now I have a flat shape, but the area is again 1, right? If I increase delta. If I decrease delta, now I have a steep shape, but the area is again 1, right? Shaded area is all 1 in those cases. So as delta goes to infinity, as delta goes to 0, what happens? This curve is becoming more and more tall, right? So in the limit, this impulse of t is simply denoted as this. So there is an arrow here sitting at 0, and the area under this arrow is 1. So it has the height goes to infinity. So this is why there is an arrow here. The height goes to infinity, but the area is 1. So if you integrate this from, let's say, minus 1 to plus 1, impulse of t dt is always 1. It is 1. So just like this one, right? I'm decreasing delta more and more. So this 1 over delta is going to, let's say, infinity, and this delta is going to 0. So the area is always 1 for this case. And in the limit, I have impulse of t. What about ut? Remember my u delta t? It was this, right? So if you decrease delta to 0, you simply have this u of t. This is 1. So that's it. And it is ut is 0 for t smaller than 0, and it is 1 for t larger than 0. So I have some very important properties. First one is this. Impulse t is derivative of ut. So dut by dt is simply delta t. And delta t is equal to 0 if t is not 0. And if you integrate it from t1 to t2, so if you integrate delta from t1 to t2, so let's once more draw this impulse. It is If you integrate this from t1 to t2, what do you expect? If, let's say, t1 is here and t2 is here, this interval does not cover origin. So since it does not cover origin, the integration is 0. But if let's say t1 is here and t2 is here, if the interval covers the origin, then in this case the integration is 1. If t1 and t2 interval covers the origin, okay, and it is 0 else. What is next? Ut is, well, this is a direct consequence of this. Of course, if you derivate ut and get impulse of t, if you integrate impulse of t, you get ut. You can again visualize it as this. Let's draw here impulse of t. This is 0. So I'm taking the integral, right? From minus infinity to some t, right? So there is t here, and I am taking the integral in this interval. So if, of course, this t is a negative number, then delta t is 0 here, so the integration gives me a 0. So when this t passes the origin, so when I take the integral from minus infinity to t, since this interval has the delta function, the result is 1. So this is simply ut, and it is equal to 1 if t is larger than 0, and it is 0 else. Okay. Then next thing is x of t times impulse of t minus t0, and this is a direct dual of this discrete case. This is x of t0 times impulse of t minus t0, as expected. And in the next one, again, this is a dual of the discrete case. You multiply and integrate. So if you do this, you get instead of a signal, you get a number. So it is simply equal to x of t0 if t1 smaller than t0 is smaller than t2, and it is 0 else. Okay, so this is simple. Well, these are again your exercise. Please try them at home. Well, at this point, I have a square type example. Let me draw it. So 1, 2, 3, 4. So in the interval 1 to 2, it is 2. Then it is here -1. That's +1, +2 again. Sorry, it was +1. Let's erase this. So this is my signal, x of t. What about x prime of t? If you take the derivative to t, then this is what you get. Well, the signal is 0 in the interval 0 to 1. Then there's a sudden jump, right? You see the signal is increased by 2 units. Then it means that at 1, I have here a delta, and this delta has area of 2. Then what happens? It is constant in the interval 1 to 2. So in the interval 1 to 2, since the signal does not change, again the derivative is 0. Then it decreases from +2 to -1. So there's a let's say a decrease in amount 3. So I have an impulse with area -3. Then again, from -1 to 1, there's an increase. So at 4, again, I have another impulse with height. Sorry, at 4, again, I have another impulse of height 2. So this is the actually concept of impulses and unit impulse and unit step signals. If you take the derivative of ut, then you get that delta function. So, well, I hope unit discrete time and continuous time, unit step and unit impulse functions are clear. Now we will make a very brief overview of complex algebra and arithmetic. First one is Euler's relation. Well, it tells you that if you have e to the j power theta, this is nothing but cosine theta plus j sine theta. So this is what Euler's relation tells you. If you have e to the power minus j theta, of course, instead of theta now I have minus theta. So it's equal to cosine minus theta plus j sine minus theta. And you know that cosine is an even function, sine is an odd function. So cosine minus theta is cosine theta, and sine is an odd function. So sine minus theta is minus sine theta. This is minus j sine theta. This was in Cartesian form. What about in polar form? In polar form, I represent numbers with magnitude and with angle. So r and theta are my magnitudes and angles, respectively. Well, how they are related, how polar and Cartesian forms or rectangular forms are related. This is my, let's say this is my real axis, this is my imaginary axis, and I have this x plus j y here. So I have, this is theta, so I have x plus yj here. So this is my complex number. What is r? R is simply square root of x squared plus y squared, and theta is simply tangent inverse y over x. So from this, of course, we can obtain x is equal to r cosine theta and y is equal to r sine theta. So these are the relationships between rectangular and polar forms. What about complex conjugates of a complex number? Well, if you have z is equal to x plus jy, then z conjugate is simply x minus jy, and this is, if this is equal to r e to the j theta, this is simply equal to r e to the minus j theta. So I simply inverse the angle in while calculating complex conjugates. What about complex arithmetic? So if I have two complex numbers, let's say r1 e to the power j theta 1 and equal to x1 plus jy1, I have z2 which is equal to r2 e to the power j theta 2. This is equal to, let's say, x2 plus jy2. Once I define those, then z1 plus z2 is simply x1 plus x2 plus jy1 plus y2. So that's simple. When I so if I continue to write this in polar form, this is equal to x1 plus x2 squared plus y1 plus y2 squared in square roots times e to the power j tangent inverse y1 plus y2 over x1 plus x2. Okay, so this is the radius or magnitude of the new sum, and this is the angle. So while summation, you know that you realize that it is simple to use the rectangular form, but when you multiply z1 and z2, of course you multiply magnitudes and you sum the angles. So that's it. So this is how we perform complex arithmetic. Well, next thing that we will discuss is complex exponential signals. Well, the continuous time complex exponential signals is of the form x of t is equal c times e to the power at. Well, of course, in general, both c and a are complex numbers. Well, if we start with real exponential signals, in that case, if c and a are both real numbers, then we have real exponential signals. So both c and a are real. Well, if a is larger than 0, then I have a growing exponential. So this is my growing exponential. On the other hand, if alpha is smaller than 0, then in that case, I have a decaying exponential. So this is for real signals. Well, what about periodic complex exponential and sinusoidal signals? If a is purely imaginary, then let's define a is equal to j omega 0. If a is purely imaginary, then in that case, of course, x of t is simply c times e to the power j omega 0 t. And this brings me c times cosine omega 0 t plus j sine omega 0 t. So what's the meaning of this? There is times c. What's the meaning of this? It tells you that you have a sum of cosine and sine. So c is real, a is purely imaginary. So this is real. So this is a purely imaginary signal as written. So of course omega 0 is real. Then in that case, I have a periodic complex exponential. Well, what's the period of this signal e to the power j omega 0 t? What's the period of this? It is simply 2 pi over omega 0. So how can I prove this? Please remember that x of t is equal to, if x of t is a periodic signal, it's equal to t plus capital T for all t values, and t is element of real plus, right? So if this is the case, I can find a period t for the signal. So let's check. If e to the power j omega 0 is periodic, then it must be equal to, so e to the power j omega 0 t must be equal to e to the power j omega 0 t plus capital T. And I know that this is equal to simply e to the power j omega 0 t plus 2 pi, right? I know that this sinusoidal signals are periodic with 2 pi, so this is what I have. So from those two, omega 0 t is equal to 2. Omega 0 is simply equal to 2 pi over, period t is equal to 2 pi over omega 0. Okay, so this is my period t0. Well, e to the power j omega 0 t and e to the power minus j omega 0 t have the same fundamental period. Remember fundamental period concept? Actually, if a signal is periodic with t, it is periodic with any integer multiple of t, right? It's periodic with 2t, 3t, 4t, and etc. So in that case, if I multiply this with, let's say, k, this is again multiplied with k. So actually, this e to the power j omega 0 t is periodic with any multiple of 2 pi over omega 0. But the smallest one, which means that the fundamental period is simply 2 pi over omega 0. Well, when I write x of t in this form, actually I can relate somehow cosine a chi cosine omega 0 t and a sine omega 0 t. So how can I write this? First, note that let's write a xi of t as a cosine omega 0 t, and this is nothing but real part of a times e to the power j omega 0 t. That's simple. A times e to the power j omega 0 t is, you know, a times cosine omega 0 t plus a times j sine omega 0 t if you use Euler's relationship. So the real part is this one. So this is my xa of t. What about xb of t? It is a times sine omega 0 t, and it is equal to 1 over j imaginary part of a0j omega 0 t. So this is the imaginary part. So if I take the imaginary part and divide by 1 over j, then I have xb of t. Well, now as a next step, let's define fundamental frequency as omega 0, so which is 2 pi over t0. Well, I say fundamental frequency once more. Note that any multiple of 2 pi omega 0 t is again a period of my complex exponential, but as a fundamental frequency, I mean the smallest of those periods. So the smallest of periods is fundamental period, and if I divide 2 pi by fundamental period, I have fundamental frequency. So, well, the units of t0 and omega 0. So if t0 is in seconds, then omega 0 is in radians per seconds. Okay. Then I can define a set of harmonically related complex exponentials xk of t that's defined as e to the power jk omega 0 t. So now I define here k times omega 0, and all of them actually the fundamental period of any of them e to the power jk omega 0 t is simply 2 pi over k omega 0. And of course, if you assume omega 0 is positive, so remember omega 0 is a positive number, so I get rid of those absolute numbers from the previous page, and all of them is periodic with 2 pi over omega 0. Okay, so this 2 pi over k omega 0 is the fundamental period for all of those e to the power jk omega 0 t type exponentials, and 2 pi over omega 0 is the common period of all of those signals. So at this point, let's try to plot this one real, let's say xk of t. Let me plot this one, cosine k omega 0 t. I will draw this for k equals 1, 2, and 3. At least I will try to do this. So let me do my best to draw this. So this is my 2, 0. Let's say this is minus t0, and is equal to 2 pi over omega 0. So you see that this is the period of the signal. So it does one cycle, then repeats itself again, right? So it does one cycle here, and once more repeats itself. So actually, let's draw the origin to the correct location. Okay, so this is better. So let's say this is x1 of t. So x2 of t, since there is a 2 here, for x2 of t, it will have a smaller period. So it is a faster signal. So x of cosine 2 omega 0 t has period at 2 pi over 2 omega 0. So it is at pi over omega 0. So here, let's say at pi over omega 0, I have the period of x2 of t. So let's draw x2 of t. So it is as this. So this is my x2 of t. So it is 2 times faster than my, let's say, x1 of t. What about x3 of t? Now x3 of t has period 2 pi over 3 omega 0. So it is 2 pi over 3 omega 0, 3 omega 0. So it is, let's say here, 2 pi over 3 omega 0. So it will finish its cycle within this 2 pi over 3 omega 0 periods. So all of them has the common period 2 pi over omega 0. So the individual signals has individual fundamental periods, but all of them are periodic with this 2 pi over omega 0. So what about sum of two complex exponentials? Let's say I have x of t. Sorry. So I have x of t defined as e to the power j t plus e to the power j 3t. Then, in order to sum them, I get e to the power j 2.5t parentheses. Then in this form, I have e to the power j minus 0.5t plus e to the power j 0.5t. This is equal to e to the power j 2.5t times 2 cosine 0.5t by using Euler's relationship. So this is equal to e to the power j 5 over 2t times 2 cosine t over 2. Well, in order to obtain from this to this, I used Euler's relationship. So that's simple. Well, that's all for today's lecture. Now I will be grateful if you can ask your questions.